Good morning, everybody. Welcome back after a long break. Didn't see you guys on Friday, didn't see you on Tuesday. We can start with some green check marks and make sure everybody's with us, and then we shall continue on. Today we're actually starting Unit 4, which is the beginning of the chemistry unit. So just kind of recap what we've gone through. We've done the biology, which was units 1, 2, and 3 together. And then we jumped into unit 10 because we knew we could finish that off before March break. So unit 10 was the earth science, earthquakes, volcanoes, plate tectonics. And so those are the 4 units we've done so far. We're going to take a step backwards into unit 4. So unit 4, 5, and 6 make up the chemistry unit. And then we have units 7 and 8 left, which are radioactivity and physics. So that's kind of where we're at. We're doing okay for time. We're at a good spot, which is nice. I hope to spend a little bit more time on chapter for unit 4 in chemistry than we have been on the previous units. I say that, but at the same time, there's a absolute ton of information in these chemistry units. It's a really big section. So even though we'll be going slower, it's not like, oh, we can just relax. No, there's just as much information as normal. We'll just be going through it at a bit of a slower pace. And I don't love how these 3 chapters, or units 4, 5, and 6, are set up in the course. So I'm going to kind of bounce around a bit, and I'll try to indicate when I'm moving away from the direction of the course. Just like today, we're going to go through the notes in a bit of a different order than they're presented in the learning guide. And then I'm going to jump around doing a lot more examples than are given in the learning guide, because I feel like there's not a ton in there. We should definitely be looking at some additional ones. So that's kind of where we're at, where we're going. We have class today. We're actually going to have class tomorrow. I know the schedule said that you guys will have socials all morning, but we're going to have socials first, and then afterwards you'll have some science tomorrow. So we just have 2 short blocks, one today, one tomorrow. So that's kind of it. Looks like just about everyone who's here is here, and that's good to see. Hopefully you guys had a great break, but we're just going to jump into it. So we're in Unit 4. This is the notes that go along with the Unit 4 learning guide. So we're progressing the same as we did for all the other units. And we're talking about chemistry. So here we go. Just a brief introduction. Atoms, you've talked about before in grade 9. Atoms, they can form compounds. So we're going to be looking at the periodic table today. We're going to not be talking about how compounds are formed, but just looking at atoms on their own for now. So a couple examples. Talk about elements. Elements are all of those things in the periodic table. So we have all of the elements, hydrogen, helium, lithium, beryllium, all across the periodic table. And then you can have pure substances where you have just one element, like oxygen, or you can have a pure substance made of a compound, like water. Water has H2O, so 2 hydrogens for every 1 oxygen. That can produce a compound, which is also a pure substance. So you spend a lot of time in grade 8, talking about the difference between a chemical change and a physical change. And majority of the things we talk about in the chemistry unit will all be chemical changes. So there you go. This chart is pretty important. It's a good little summary of everything. The symbols we're going to use for the subatomic particles are protons, neutrons, and electrons. So a P with a little plus sign next to it, that's going to give us our protons. And an N with a little 0 next to it, that's going to be what we use to represent neutrons. And then E with a little negative sign next to it gives us electrons. And the reason we put those little symbols next to those is protons have a positive charge, neutrons have no charge, they're neutral, and electrons have a negative charge. So we're going to spend a lot of time looking at these things today and how they work. So this might be the most important slide of the day. This is, if you can wrap your head around all of the things on this page, then you will be doing just fine. If you are going to struggle with chemistry as a whole, it's because you didn't understand what we're talking about on this page. So this is kind of the make or break point for Science 10 chemistry. I know it's kind of putting all of our eggs in one basket and seems like oversimplification, but it's so true. So we have an atom. This is our atom here. In the middle, we have the nucleus. The nucleus is where the protons, which have a positive charge, the red ones here, and the neutrons, which are the blue ones. This is where they live, in the middle. And around the outside, you have these little electrons, and they buzz around. And these are kind of really important ideas. Now, the image that we use here with the kind of classic atom that you think about isn't actually what it really looks like. If you want to think of like a fan in maybe you have a ceiling fan in your house, or if, like on a really hot day you have like a little oscillating fan. You know how the blades, when they're stopped, you can see them really well? Those are the blades of the fan. When the fan's spinning really fast, you can't really see any one blade in particular, but you can see just kind of where the blades are. It's kind of like a cloud of blades almost. That's what actually happens with electrons. They aren't in nice orbits like planets. They exist in clouds. So they're zipping around really, really fast. You're never really sure where they are, but you know the kind of the shape that they make. So that's kind of something that a lot of people don't understand about the atom, is that you have these pictures that you always see that are really simplified versions of what an atom looks like, so we can figure out where everything is, but that's not what actually happens. Another thing is the relative size of these things is never really drawn to scale. So, if we took this atom and we blew it up to the size of a stadium, like I'm not talking a stadium like in Kelowna, like Prospera Place, I'm talking like GM Place in Vancouver, or Rogers Centre, whatever it's called, or BC Place Stadium, like a big, big stadium. So if we took an atom and we blew it up, so this little picture, we took this atom, we blew it up to the size of a stadium. And this nucleus here was at the center ice in the stadium. We placed the nucleus on center ice. How big do you think the nucleus would be at center ice? Would it be the size of like a big building, like a school inside the stadium? Would it be the size of a house? Would it be the size of a car or something smaller than that? What do you think? Anyone want to take a guess as to what the nucleus of an atom would look like in terms of size if it were blown up to the size of a stadium? Isn't it pretty small? Yes, it's pretty small. Does anybody want to take a guess as to how small it would be? A car is smaller. Yes, Taylor and Abby are both on the right track here. So if you took an atom and you blew it up to the size of a stadium, at center ice, the nucleus would be about the size of a quarter resting on center ice. So we're talking really, really small. And an electron, that electron wouldn't be in the actual ice rink. It wouldn't even be in the seats. It would be outside of the stadium in a little patch of grass on the outside of the stadium. And the actual electron size would be about the size of a tip of a blade of grass outside of the stadium. So the atoms that make up you and me and everything around us, they're mainly space. You have this nucleus in the middle, about the size of a quarter, and the electrons buzzing around the outside. Those things are in the parking lot. So atoms are just space, which is kind of amazing to think that, you know, my hands are made of these atoms, and why can't I just put my hands through one another if they're just made of space? There's some other things going on here, but atoms are mainly space. So when you see these pictures, know that it's not an accurate sort of representation of an atom. It's just a really simplified version. All right, so enough of that. Number of protons equals the number of electrons in an atom. So if you look at the picture here, you see there's 3 positive charges in the middle, and that means there'll be 3 negative charges around the outside. And every time we talk about an atom, that is always the case. So if you have 5 protons in your atom, you'll have 5 electrons. If you have 100 protons in your atom, you will have 100 electrons. It is how it works. The charges need to balance out. They don't always. We'll talk about how they don't balance out later, but when we're talking about atoms, the number of protons is always the same as the number of electrons. That's extremely important. The nuclear charge is the number of protons, which is also called the atomic number. So you can see that nuclear charge equals charge of the nucleus equals number of protons equals atomic number equals number of electrons. These things are all the same. So it's like 5 different terms for the same thing. So if I say atomic number, that's the number of protons. If I say number of protons, that's the same thing as the atomic number, which is the same thing as the number of electrons in an atom. You're thinking, why do we have so many words for the same thing? Well, in different circumstances, we're going to use different words. So I have with me here the periodic table of the elements. This is right out of your data booklet. So if you guys have printed off a data booklet, which you have because you need it for all your tests, you can see right in the middle in the top center is the image I have down here. So this atomic number little diagram. So this is the key for the periodic table. Sorry, I jumped backwards. So on your periodic table, it tells you exactly what everything is, which is really nice. So this is one less thing you need to remember. Atomic number is in the top left corner of your periodic table. And in the case of our periodic table, every top left corner is the atomic number, which is nice. That's how atoms are arranged on the periodic tables, with atomic number. So the atomic number is the same thing as the number of protons. So in titanium, the atomic number is 22. That means it has 22 protons. If I asked you how many electrons that atom had, you would say 22, because the number of protons is the same as the atomic number, which is the same as the number of electrons in an atom. Ion charges we're not going to talk about today. We'll probably get to those maybe tomorrow. We might get it today. Symbol, Ti, titanium names, titanium. Atomic mass is a little bit different, so we'll get to that in a second. Does anybody have any questions about this? About the nucleus, about protons, neutrons, electrons, anything like that? Super important idea for you guys to remember the information on here. And know that if you can remember the atomic number is the same thing as the number of protons, that's just given to you right on your periodic table. So that's kind of a nice. This is a good review. That's good. I never really know what people remember from grade 9 or not, so I kind of take a step back and try to give it all to you all over again. So elements are listed by atomic number on the periodic table. And remember, atomic number is the number of protons. So if I had an atom with 1 proton, it'd be hydrogen. If I give you another proton, it becomes helium. I give you another one, it becomes lithium, then beryllium, and then all the way up the periodic table. So each element has a unique number of protons. We usually organize everything with metals on the left, non-metals on the right, and then we have the metalloids, which are kind of like metals, kind of like non-metals. They make a little staircase in the middle, and you'll see your periodic table has a nice dark black line to show you that staircase. So some other terminology that we talk about is a row on the periodic table. So going across a row is called a period. And when we talk about columns, we can call them groups, or sometimes we'll call them families. So there are 4 families we need to know on the periodic table. And the great thing is that the periodic table just has these families listed right on the bottom, so we don't have to memorize them. They're just there for us. So if you look at your periodic table, hopefully you have one nearby. Right at the bottom, and I'll show you this again in a second when I supersize this, at the bottom of the first column, the first family, it says alkali metals. At the bottom of the second, it says alkaline earth metals. And then we jump all the way across. The last 2 columns are the halogens and the noble gases. So those are all listed on your periodic table. And you don't have to memorize those things. They're just there, which is great. So, Taylor, I'm with you. I think the periodic table is probably one of the most well-organized, most intricate, amazing things that science has ever created. The amount of information and the amount of trends and the amount of things that happen in a periodic table is just, it's just mind-blowing. And we'll get into a bunch of them today in terms of looking at some of these things in the periodic table. So here you go. Here is your periodic table right out of your data booklet. You can see down at the bottom, the first group is called the alkaline metals, and we have the alkaline earth metals. Now, one slightly confusing thing about this periodic table is that hydrogen, first element, element number 1, hydrogen, this red guy up here at the top, it appears on both ends of the periodic table. Well, that's confusing. Well, it is and it isn't. Sometimes hydrogen behaves like a metal. Sometimes it behaves like a non-metal. Hydrogen is just one proton and one electron. So it sometimes can act like metal and sometimes non-metal. So just depending on what it's acting like, it gets put on both sides. Yeah, one's a +1, one's a -1. So when it's acting like a metal, it has a charge of +1. When it's acting like a non-metal, it has a charge of -1. So that's about the most complicated thing about this. Then everything else is pretty straightforward and probably what you've seen before in terms of periodic table. When we talk about periods or talking about rows in the periodic table, the first row is kind of confusing. It's hydrogen and helium. That's the first row if you go across. And then the next row starts at lithium, it goes across and it skips this gap in the middle, and then it goes across from boron, carbon, nitrogen, oxygen, fluorine, neon. Then the third period, sodium, magnesium, all the way across to argon, and then the fourth, and then the fifth, and the sixth, and the seventh. So even though there's a space, there's that gap in the middle, we still jump across the gap, and when we talk about periods in the periodic table, we'll start at the left, and we'll jump across the gap, and then we'll go to the right. And that's how we talk about those periods there. Now, it's probably not likely that you've ever seen a periodic table like this one, but this is what a periodic table actually looks like. If you were to have a really giant piece of paper, this is what your periodic table would look like. So for the purposes of saving space, what scientists have done is they've taken the elements, starting here, 57 and 89, this little chunk, these pink ones in the middle, they've taken these out. We call them the lanthanides and the actinides. We've taken them out, and what we've done is we've dropped them down below. So there's all this stuff kind of behind me here. These are all that middle part of the periodic table, but you can see that it wouldn't fit on a page if we, cut that down the middle and spaced it out. So one thing to note is everything kind of goes up in atomic numbers. So if we look at potassium's 19, calcium's 20, 21, 22, 23, 24, all the way across, it works. 36, then we start at 37. If you go down to cesium here at the bottom, you have 55, 56, 57 at lanthanum, and then it goes to 72. Well, that doesn't make sense. But if you were to jump from 57 down here to 58, all the way across to 71 at the end, and then go back up here to 72, all the way across, then you get to 86, 87, 88, 89, to 104. Oops, you got to go down and then across to 103, and then start back up here at 104. So if you were to cut that periodic table right down here, you'd end up with a periodic table that looked like this. So the only reason we have those two bars down at the bottom, they're kind of removed from the periodic table, it just doesn't fit on a page very well when they're in there. So in your brain, this is what the periodic table looks like. To put it on a page, we cut out those two groups and we put them down at the bottom. So there you go. That's what a real periodic table looks like, but it just doesn't fit on the page very well. I want to go back. I think I missed something. Atomic number on this nucleus page. I'm not sure why it's not in here, but it should be. feel like adding it right now. Let's do that. Let's add it. Let me edit this. No, of course not. I'm going to jump right back to my original here and jump back up right here. So the atomic number, I'm not sure why it's not in here, but it's not. Atomic mass is the number of protons plus neutrons. Move that over a little bit. All right. So back to the most important slide of Science 10. I added this down at the bottom. You'll have to add it to your notes. I'm not sure why atomic mass isn't in there, but in order for me to move on, I need to have it in there. So atomic mass is the number of protons and neutrons together. The atomic mass is the mass of the nucleus. That's just saying how many protons and neutrons are together in the nucleus. So for the example that we have here is titanium. You can see the atomic mass is 47.9. So just behind me here. So this is kind of the tricky part, and I'm sure your Science 9 teacher beat this idea to death. Hopefully you remember it. The atomic number is the number of protons up at the top here. The atomic mass is protons and neutrons. So when we have the atomic number being 22 and we have the atomic mass being 47.9, we'll round that 47.9 up to 48. And what we can do is we can figure out how many neutrons there are. Nowhere on the periodic table does it directly tell you how many neutrons there are, but you can figure it out. If you know the atomic mass is protons and neutrons, and you know 22 of them are protons, well, you just need to subtract these. So 48 minus 22 it leaves us with 26 neutrons. So even though the atomic mass doesn't indicate neutrons directly, we can figure it out if we just subtract the atomic number. So we're going to use that today. That's really important. Taylor, you're asking a great question. How come some of the masses in the periodic table are in brackets? Does anyone know the answer to that question? That's a really important idea. It doesn't happen too much. Like, I don't think it'll be tested, but you can definitely, it's important to know why some of them are in brackets. It actually tells you on your periodic table in the bottom left corner. If you look there, have a little peek. The very bottom corner down here on the left side, it tells you anything in parentheses, so anything in brackets. And it reads, any value in parentheses is the mass of the most stable or best known isotope for elements which do not occur naturally. So if you see something in brackets, that means it's not a naturally occurring element, which means that the only time it ever exists is if, it exists on Earth, that is if scientists synthesize it and make it artificially. So when you see some of these, especially along the bottom row, these really, really heavy elements along the bottom row, they're all in brackets. So these are not naturally occurring elements. We create them in a laboratory. They last for like a billionth of a second, and we say, oh, there it was. For a billionth of a second, we created, and then insert any one of these things here. So the periodic table, if you see something in parentheses, is just not naturally occurring. It only happens in a laboratory. How can there be a decimal atomic mass? I'm glad somebody was paying attention. Why would it be, first of all, let's take a step back. Why does that seem strange? Why couldn't we have a decimal atomic mass? Now, you might have learned it, probably not though. So how can we have an atomic mass that's a decimal? Let's think about the atomic mass again. The atomic mass is the number of protons and neutrons added together. So for some of the elements, like the one behind me here, we have titanium is 47.9. How do you have 0.9 of a proton or a neutron? How does that work? Can you have half of a proton or half of a neutron? Well, the answer to that is no. So you can't have half a neutron or half a proton. Let's look at some of these elements. I'll just take a step forward to my periodic table. Some of the elements you can see here, let's pick a good one, like hydrogen at the very top, number 1, it has a mass of 1. It's just a proton. Like beryllium, number 4 here, it's right above my head, it has an atomic mass of 9.0. So that's good. Then when you start going across the periodic table, boron has 10.8, carbon's 12, nitrogen's 14. In the middle of the periodic table, things get a little bit wonky. So, you have all sorts of decimals in there. Does anyone remember why we have those decimals for the atomic mass? Because it's a completely important question to ask, because you shouldn't have decimals because it's just protons and neutrons. How do you have half a neutron or 0.2 of a proton? It just doesn't make any sense. I'll take it that nobody remembers. What we're going to do later on is talk about something called isotopes. And it's possible that you've heard of the word before but never really fully understood what it means. Isotopes are the same element that just have different numbers of neutrons. So really popular one is potassium, not popular, one that we'll talk about, I should say. So number 19, just right above my head here. Potassium has an atomic mass of 39.1. So there's a bunch of potassium that exists as 39. There's also some potassium that exists as 38. There's some potassium that exists as 40. And basically we take the amount that occurs in nature, we say, how much of the potassium is the potassium 39? Well, most of it. A little bit's the potassium 40, a little bit's the potassium 38, and we just round it all off and take the average of everything that exists in nature, and then we basically just we write the average that exists naturally. So some atoms will have isotopes and others won't. For now, we don't want to talk about isotopes. We're not quite there yet. It's not a gross estimate. It's very precise. So the word estimate's not really a great word, but it is an average for the naturally occurring ones. So for the purposes of Science 10, for the next 2 or 3 weeks, if you see a mass in the periodic table, you're going to just round it. So if you see something like potassium's 39.1, we're going to round that down to 39. If you see something like bromine, number 35, way over here, 79.9, well, that's going to get rounded up to 80. So for everything we do for the next few weeks, we're just going to round all those masses. If it's a 0.5, it rounds up. Anything below 0.5, it's going to round down. All right, so here we go. This kind of jumps around in your notes, and I tried to indicate that. We're going to spend a little bit of time talking about Bohr models. Anybody talked about Bohr models before? It's possible that you've seen these things in grade 9. I explained not very well, Abby, when I just said, hey, we'll look at it later. But yeah, it has to do with isotopes. And I promise you, you will fully understand it later on. If you take Chemistry 11, you'll spend a lot of time looking at it. Bohr models. Did anybody talk about Bohr models or understand what a Bohr model is? Maybe you've heard the name before, the word before. It's always nice. Ava remembers Bohr models. Anna does too. That's good. Yes, yes, yes. Awesome. So there's a few of you who remember what Bohr models are, which is good. Everybody did Bohr models. So what we're going to do is Bohr models all over again. There's a lot of Bohr models in Science 10. And what we'll do is we'll talk about Bohr models, and then we'll talk about a little bit of easier way to describe what these atoms look like using something called Lewis dot diagrams. So Bohr models were named after Niels Bohr, and he had a bunch of middle names, but I never remember what they were. And they're, again, just really simplified versions of what atoms look like. So we're going to spend some time, yeah, Abby, you got it, perfect. We're going to spend some time looking at them. So Bohr diagrams show you how many electrons are in an atom. And the reason we care so much about electrons is because electrons are what determines how atoms are going to bond together. And that's kind of where we go from Science 9 chemistry to Science 10 chemistry. We're talking about bonding now. We're going to put some atoms together and see how they bond. So each shell or circle in a Bohr model holds a different number of electrons. And once that shell is full, the electrons go into the next shell. And you keep filling up shells until you run out of electrons. So in a Bohr model, we write these things as like a 2D picture, but it's really a three-dimensional thing. And like I said before, it's not these unique like planetary orbits. It's kind of like a fan. These things are buzzing around really quickly, and they're kind of filling what we call electron clouds that form shapes, not nice spheres like you'll see here. So those are two pictures of Bohr models on the side. So we're gonna draw a few of them now. So let's get the rules out of the way. I don't think this is in your notes. No, I wrote not in notes. I came up with this. You definitely should write this down somewhere. So you're gonna do a bunch of examples today. So it's probably worthwhile for you to just grab a piece of paper or a couple sheets of just blank paper, line paper, or whatever. And we're going to do a bunch of examples that aren't in the learning guide, and just to kind of help you guys wrap your brains around what's going on here. So, rules for Bohr models. In the middle, in this kind of gray area here, you're going to put the number of neutrons and the number of protons are going to go in here. Sorry. And then we're going to put the electrons in the rings around the outside. So we're going to draw the electrons as just dots. So in order to figure out where the electrons go, looking at number 4 here, what we're going to do is remember that the first shell holds 2 electrons, then the second shell holds 8, and then the third shell holds 8. And in Science 10, you will never have to go past argon with your Bohr models. Bohr models kind of fall apart after argon because the orbitals no longer kind of spherical. They change shapes. And that's chemistry 11 stuff. So the first 18 elements you're kind of responsible for. So you should be able to draw the Bohr model for any element between 1 and 18. So the example at the bottom says try and draw the Bohr model for an atom of oxygen. So that's what we're going to do right now. And again, this isn't in your notes. You're going to need to grab a piece of paper and actually do this. Now, kind of like math, when I'm going through the problems, it's really easy to sit there and just copy down what I'm doing and be like, oh yeah, I get it, that looked really easy. It is so important that you are actually doing these things, actually drawing them, because if you just watch me do it and then try to do it on your own, it becomes really difficult. There's a lot of really tricky things in here. So I can't stress it enough. You're going to get out of this what you put into it. If you just sit there and you're kind of an observer, you won't really master this topic. But if you actually grab a pencil or pen, start drawing these diagrams with me, you should be doing just fine. If you do have questions or are confused, make sure you let me know. So what I'm going to do is I'm going to jump over to periodic table here. I'm actually going to draw the Bohr model with you guys. So the example we were wanting to do was oxygen. So I'm going to find oxygen on the periodic table. Here it is up here. And you can see that oxygen has this 8 up in the top corner. And I want you to remember what that 8 represents. That 8 is the number of protons. And when I write protons, I'll write it as P with a plus sign. Do we write down the rules? If you remember them from last year, maybe you don't need to write them down. If you don't remember them, definitely write them down. I'll go back to them in a second. Promise. So the 8 is the number of protons, which is important. Down at the bottom, we have the 16. And remember the 16 is protons and neutrons, which is an N with a little 0 next to it. So if I have 8 protons and I have 16 protons and neutrons added together, how many neutrons do I have? You will do this a million times in Science 10. Can anybody tell me how many neutrons we have? What do you think? Seems pretty straightforward, of course, and it is. 8, yeah. So we have 8 neutrons. Sometimes the protons and neutrons will be the same. Sometimes they won't. So in order to figure it out, what you can do is take the atomic mass and you can subtract the atomic number. So what I'm going to do is take that 16, which was the atomic mass. I'm going to go 16 minus 8, and I'm going to end up with 8, which is the number of the number of neutrons. So again, the 16 represents protons and neutrons together in the nucleus. The 16 tells you how massive the nucleus, how much weight the nucleus has. And we know that the atomic number of that element is 8. So if 8 of those things in the middle, 8 of the 16 are protons, what's left? Well, there has to be 8 neutrons as well. So what I'm going to do is I'm just going to jump to a blank page here. So we want the Bohr model for oxygen. All right. So we found that the atomic number for oxygen was 8. So we know it has 8 protons. And we did a calculation. The mass was 16. So we went 16 minus 8. And that gave us 8 neutrons. So I'm going to put that in the middle of my Bohr model. I'm going to apologize in advance for my circles for my Bohr model. They're not going to be great. All right. So going back to the most important slide in Chemistry Science 10, one of the ideas on there was how many electrons there were. So if I have 8 protons, how many electrons do I have? In an atom, we have the same number of protons as electrons. The charges are going to balance. We have 8 positive charges, we have to have 8 negative charges. So in this case, oxygen has 8 protons, it'll also have 8 electrons. Now, for a Bohr model, we need to remember the rules. The first shell, which we're going to start with, we're going to start at the inside and work our way out. The first shell can hold a maximum of 2. So I'm going to put 1 electron here, and then 1 here. So there are my 2 electrons in my first shell. That first shell is now full. I can't put any more electrons in it because it can only hold 2. So if I run out of room, I have to draw another shell. All right, so oxygen has 8 electrons. I have 2 in the first shell. That means that there's room for 6 in the second shell. Now, when I draw the electrons, I'll always put them at the compass north, south, east, west, just to kind of make things a little bit neat and tidy. So there's 3 now. There's 4, 5, 6. And then I know I have 8. So I'll start back again. There's 7, and then 8. So I have 1, 2 on the inside, 3, 4, 5, 6, 7, 8. I have 8 protons, 8 positive charges in the middle. I have 8 electrons or little dots around the outside. So this is the Bohr model for oxygen. This is what it looks like. Now, yeah, that's good. Does anybody have any questions about that? And again, it's really easy for you to just sit there and be like, that looks pretty straightforward. You just drew some circles and put some dots on it. I can do that. But it's extremely, extremely important that you guys try this along with me. Why doesn't somebody pick a number between 1 and 18? And we'll do one more example. First number between 1 and 18 that appears in chat, we're going to do that one. Anybody? 17, I like it. I like 17. So 17 is chlorine. So let's draw the Bohr model for chlorine. And just scroll this down a little bit. All right, so chlorine's number 17 on the periodic table. Maybe I'll just jump over to a periodic table here. Get rid of all this. All right, let's find chlorine first of all. Here it is, 17. That yellow doesn't show up very well. There we go. Element number 17, chlorine. The atomic number is 17 and the mass is 35.5. And we're going to round that 35.5 to 36. All right, so the atomic number is 17. The mass is 36. So I'll jump back to this blank here. Atomic number, 17. Atomic mass is 35.5, which we're going to round to 36. So remember, to get the number of neutrons, and that's N with a little 0 next to it because they're neutral. To get the number of neutrons, we're going to take the atomic mass, which is 36, and we're going to subtract from it 17. And remember, the mass is protons and neutrons in the nucleus. We know that 17 of those things in the middle are protons, so what's left? So 36 minus 17. What do we think? There's no shame in using your calculator. I brought mine along with me. Once you get into the heavier elements, the numbers get really, really big. So just looking at something like mercury, that has 201 mass and 80 protons. I mean, doing the math in your head, there's no requirement. On your Science 10 tests and provincial exam, you're allowed to use a calculator. So use it. If you're not good at math, that's fine. There's no point in penalizing yourself for not being good at math in a science class. So 36 minus 17 gives us 19. So the number of neutrons is 19. All right. Good. A lot of mental math happening here. I like it. So when we draw our Bohr model, we're going to start with the nucleus. Now the atomic number is 17, so that means there's 17 protons. Remember, the atomic number and the number of protons is the same thing. All right, in the middle we also put the number of neutrons. So we had 17 protons and 19 neutrons. And the number of protons and neutrons is not necessarily going to be the same number. It's possible for these things to be different. They'll always be close to the same, but they don't have to be exactly the same. All right, so that's my nucleus. I'm going to write a little circle around that, and we'll just leave it like that for now. Now we need to figure out how many electrons there are. So does anybody remember how we figure out the electrons in an atom? If we have 17 protons, how many electrons do we have? 17. I see a vote for 17 from Avery. I like it. And Avery, you are perfectly correct. So if we have an atomic mass or atomic number of 17, in an atom, the number of electrons, or E minus, is equal to the number of protons, or P plus. Perfect. You guys are all on this. I'm hoping this is a review for a lot of you. So if we have 17 protons, that means we have 17 electrons. They're the same in an atom, which is really good. All right, so let's start filling our shells. The first shell can hold a maximum of 2. So let's fill it. I'm going to start here. I'll put one down at the bottom. I know I said use like cardinal, north, south, east, west, but I kind of like splitting those two up. Nice and symmetric that way. All right, so there's my first shell, holds a maximum of 2. Draw the next shell. All right, so the next shell can hold 8. And we have 17, so we have a bit of a ways to go. So there's 3, there's 4, there's 5, there's 6, 7, 8, 9, and 10. So the first 2 shells can hold a maximum of 10. 2 in the first shell, 8 in the second. So we have 17 electrons. We've accounted for 10 of them, so we still need to draw one more shell. That shell's now full. So let's go to the next shell. Ooh, that was not a good circle. That's okay. The next shell, I have 10 so far, so there's 11, there's 12, 13, 14, 15, 16, 17. All right. So that's it. That's the Bohr model for chlorine. It has 17 protons, it has 19 neutrons, and it has 17 electrons. Remember, 2 in the first shell, you can get 8 in the second shell, and then the third shell will hold a maximum of 8. But we didn't need all of them because we only had 7 in the third shell. So does anybody have any questions about Bohr models? We're going to maybe cruise on a little bit into the notes, and we'll come back to Bohr models in a little bit. What are the rules for the next shells? Yeah, everyone always wants to know, what's the rule for the next shell, Mr. Borden? Science 10, we're only concerned about the first 3 shells. Once you get past those shells, the rules get a little bit trickier because the shells aren't nice spherical shells. They become kind of weird shapes. So we don't actually go past that. So we'll go up to 18 in Science 10, and that's it. What's not to like about that, hey? Yeah, let's go back to those rules. Let's see if I can fire those up. So, periodic table, no, let's try this. There we go. All right, so the number of protons goes in the center, we did that. The neutral atom, the number of protons is going to be the same as the number of electrons. So we did both those things. The neutrons go in the center as well. So in that gray circle, we have protons and we have neutrons. Perfect. Electrons go into the outer shells as dots. And we start the shells filled from the inside out. So 2 in the first shell, 8 in the second shell, 8 in the third shell. Abby, that's another good question. Abby, you have nothing but good questions. Have we proven that this is how atoms work, or is this theory? This is all theory. Now, the problem with electrons is they're really, really small. And we can't visually observe them. We can use them to do lots of things. We think they're there. We can control them. But it's kind of hard to prove that all of this stuff is happening because it's just really tiny. So we call it atomic theory. And it is, we have lots of evidence to support this theory. So it's taken as the best theory that we have. That's a good question, though. Sometimes we take some of the stuff we are learning as fact, but in a lot of cases it's theory. But this is pretty well understood theory, so I don't foresee anyone disputing this theory anytime soon, but we never know. So there you go. Those are the rules. If you don't remember the rules, or if you haven't seen them for a long time, it might be worth writing them down. Or maybe even just number 4, if you just remember the protons, neutrons in the middle bit, then you can get the first shell has 2, the second shell has 8, and the third shell has 8. That would be really great. One thing that I will point out right now that we're talking about it, is the periodic table, as I said before, is just amazing. And Taylor's with me on this one. If you forget how many electrons go in the shells, I will go back to the periodic table here. And if you look at the first row, or the first period on the periodic table, how many elements are in that first row if you kind of ignore hydrogen being in 2 spots at once? How many elements do we have there? Well, we have hydrogen and we have helium. There are 2 elements in the first row on the periodic table. How many elements are in the second row? So if you started at lithium and then you cruise on across to neon, how many elements are in that row? Well, what do you know, Mr. Borden? There's 8 there. Is it a coincidence that the first shell of an electron holds 2 electrons and the first row on the periodic table has 2 elements in it? Is it a coincidence that the second row on the periodic table has 8 elements in it and that shell holds 8 electrons? Is it a coincidence that the third row on the periodic table also has 8 elements in it and that shell holds 8 electrons? No, these aren't coincidences. This is how the periodic table is arranged. We've arranged it in terms of atomic number. We put a big gap there because there's these elements down below, but the first shell holds 2, the second shell holds 8, the third shell holds 8, and you can continue that down. The next shell holds, if we count it all the way across from potassium to krypton, we'd go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 18. So for those of you who are saying, how many elements or electrons are in the next one? Yeah, it's 18. So we have 2, 8, 8, 18, 18, 36, 36, if I'm not mistaken. 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 32. 32 and 32 in the last 2 shells. In grade 11, you'll talk about the next elements past 19, or 18, sorry. So we talk about S orbitals, P orbitals, D orbitals, and F orbitals. And that's all for chemistry 11. So don't worry about it. But for science 10, we've got the first 18, long as you can remember 2, 8, 8. And if you can't, just remember that the first row has 2, the next row has 8, the next row has 8, then you're good to go with the shells. Now I apologize, we're kind of bouncing around a little bit in the notes right now. So multiplies by 4 every second one. Is that the case? 2, 4, 18. 32 is the last 2. I miscounted, I think, not 36. So that rule doesn't necessarily apply. All right, so if you can kind of go back a little bit in the notes, it starts talking about ions near the Bohr model stuff. I forget exactly what page this is on. But we're going to talk about ions now. This is where everything kind of turns into Science 10 from Science 9. In Science 9, you talked about protons, neutrons, atomic mass, atomic number. All of that stuff is things you should have covered in grade 9. Now we're going to talk about stuff that is unique to Science 10. We talk about ions. Now, the trickiest part, one of the tricky parts about chemistry is some questions you'll see say an atom of chlorine, and then some questions you'll see say an ion of chlorine. And you need to, in your brain, draw a distinction between atoms and ions. They are different things, but they refer to the same elements. So things get tricky in that regard. So atoms, they exist in nature, but they aren't happy. And when an atom becomes an ion, it just is trying to become happy. That's all it wants in life, is just to be happy. So sometimes atoms will lose or gain electrons to make their shell, their outer shell, which we call a valence shell. The last shell in a Bohr model is called a valence shell. Sometimes they're going to gain or lose electrons to have a full outer shell, to become happy. Now you're saying, Mr. Borden, how do I know if they're gaining or losing? If you want to think about it this way, atoms are really lazy. They're always going to do the easiest thing. So above me here, I have atomic number or protons of 11. So this is, if I look on my periodic table, 11 is sodium. So this is sodium. This is a Bohr model of sodium. There's 11 protons, there's 12 neutrons, and how many dots do I have? Well, if there's 11 protons, there's 11 electrons. So we have 2 in the first shell, 8 in the second shell, and then we have this one kind of hanging out by itself out here in the third shell. Now, if you are sodium, what is going to be easier for you to have a full outer shell? Are you going to try to search and try to find an additional 7 electrons to fill that outer shell? Or are you just going to say, hey, I could probably just get rid of this 1 and then have a full outer shell? So is it more likely that sodium's going to gain 7 electrons or lose 1? What seems like a simpler thing for this little sodium to do? That's good. If you've seen this in Science 9, then you're further ahead, which is awesome. Yeah, it's going to be easier to just lose 1. So if you're sodium and you lose 1, what do you look like now? Well, you look like this. You have these. You have the 11 protons still. You still have 12 neutrons, but now your number of electrons isn't the same as your number of protons. You lost that 1. So that outer shell that was out here with that 1 electron flying around the outside, you got rid of it. And you're saying, well, where did it go? Well, there's another atom around somewhere that was like, hey, I'd really love to take that electron from you. So it gave it up to somebody else, which is fine. This happens all the time. Remember, we're talking about like trillions and trillions and trillions and trillions and trillions of electrons interacting. So this just happens. There's always somebody nearby who's willing to give up an electron or take an electron. So that's how it works. So this is kind of the tricky part that maybe might not make a ton of sense in your brain. Now, the sodium down right next to me here, right there, it now doesn't have the same number of protons as it does electrons. So the protons are 11, but now the electrons are only 10. So this atom is no longer an atom. It has lost an electron, and it is now an ion. It has a charge. So if you have 11 positive charges, 11 protons in the middle, and around the outside you only have 10 negative charges. So overall, what is the total charge on this ion? You have 11 positives in the middle, you have 10 negatives on the outside. There's an imbalance between positives and negatives. Avery, I see your question. I'll get to it in just 1 second. So what is the charge on this sodium going to be? If you have 11 positives in the middle, you have 10 negatives on the outside, you end up with a charge of positive 1. You have 1 extra proton. So there's some really great questions coming in here. I should probably throw them up on the board. Avery, you're right. It has a charge of plus 1. There are 11 positive charges. There are only 10 negative charges. So you have an imbalance. You have 1 extra proton, which is fine. So Alex, you asked a great question. Since atomic number equals number of protons, then doesn't the atomic number change too? Well, if you look up above here, we have 11 protons. And down here we have 11 protons. So the number of protons did not change. If it had changed, you would be completely right, Alex. You would change the element, the atomic number would change. But we haven't changed the number of protons. It stayed the exact same. It stayed as 11. The only thing we're changing is the electrons. Now, if you think about the kind of picture of an atom, you have all these things in the middle, the nucleus, the protons and neutrons. The electrons are buzzing around the outside. The electrons are kind of flying around out there, and they're easily lost and gained because they're out on the outside. In the middle, in the nucleus, these things are kind of packed tightly in there. They're protected by all the electrons. You don't generally lose or gain protons or neutrons. It can happen, but not very often. So the number of protons and number of neutrons very rarely ever changes. There's a few exceptions, which we'll talk about at the very end of the chemistry unit. But generally speaking, the nucleus remains unchanged. For everything we're going to do for the next 2 weeks, the nucleus will always remain the same. So the idea here is that, that was Alex's question. And then Avery, why do they do that? Elements want to have a full outer shell. If we look at the periodic table, jump back here to a picture of it, the last column has this helium down through, and these are called the noble gases. And the noble gases are extremely stable. They don't bond with anything because their outer shells are full. So when we talk about atoms bonding with other things, the reactivity of an atom is determined by what's going on in the outer shell. So if you have a full outer shell, you become very stable. And all atoms want to have a full outer shell, whether that means filling it with extra electrons or getting rid of extra electrons in that outer shell. So everything's trying to look like its nearest noble gas. Sometimes it'll gain electrons to look like that, sometimes it'll lose electrons to look like that. But these noble gases are stable, and all atoms want to become stable. So it's kind of the idea behind this gaining and losing of electrons, is to become more stable. So they gain or lose to become the most stable they can, and that means looking like their closest noble gas. So I think we got most of those questions. If we added one proton to an atom, would we have just created a new element? Yes, you have. Exactly. So if you started here at, go back to that other periodic table. If you were at sodium, and you could figure out a way to throw a proton in the middle of sodium, you would end up with magnesium. You'd go from 11 to 12. And then if you had some magnesium and you said, oh, okay, I'm going to throw this one proton in the middle, you would go from 12 to 13. All of a sudden it becomes aluminum. Now, for hundreds of years, scientists tried to do this. They tried to create gold out of everything you could imagine. It was based on, they called it alchemy. And they were trying to make gold. It was a precious metal. They said, well, if we started with whatever, like the things they started with was just amazing. They started with things like human urine, elements that existed in nature, other things. They tried desperately to get these things to turn into gold, and they were very unsuccessful because it's very difficult to do this. Now, we talk about radioactivity later, which allows us to do this, but in nature it doesn't naturally sort of happen. There's no atoms just spontaneously changing into other atoms because of something we do. They happen as a result of radioactivity. Alex saying helium doesn't react. No, it doesn't. Helium doesn't react. And one really cool thing about helium is that because it doesn't react and it's not bonded with anything, helium won't react or form bonds with anything because it's really happy. It has a full outer shell. It has two spots in its outer shell, 2 electrons, it's full, it's happy. The amount of helium on Earth is finite, meaning it's not unlimited. And if you can imagine helium, it's really, really light. That's why we fill balloons with helium. It floats up into the atmosphere. So if you had a helium balloon, you popped it, the helium will escape out of that balloon and it'll float up into the atmosphere. Eventually, on Earth, we're going to run out of helium. And you're like, what? Yeah, it's happening. There will be a helium shortage. I don't know if it'll happen in your lifetime or my lifetime, but helium, because it is so light, it travels up into the atmosphere and it just disappears and it just goes away, and we're going to run out of helium because it just floats away. Pretty crazy. It's going to happen eventually. It's kind of sad. I like helium balloons. And we could fill it with things like hydrogen, but hydrogen's highly flammable. It can explode, so that's not a good idea either. What if we're wrong and helium is heavy, but it's just repelled by gravity instead of attracted to it? That's an interesting theory. I'm sure it can be disproved many, many ways. What will happen when all of the helium's gone? I don't know. We won't have helium balloons at birthday parties anymore. Be a sad day, wouldn't it? The only thing kind of lighter than helium is hydrogen, and it's flammable. I mean, maybe in like a few thousand years, people won't have balloons at birthday parties anymore. That's sad. Sad to think about it. All right. This isn't, again, in your notes, but it's important enough to figure it out. So let's talk about ions a little bit more, and we'll draw a few ions here in a second. So the example behind me is fluorine. Fluorine's atomic number 9 on the periodic table. It has a mass of 19. So if we go 19 minus 9, we end up with 10 neutrons. So that's in the nucleus there. If it has 9 protons, it has 9 electrons. So we draw the dots. 2 in the first shell, 1, 2, and then 3, 4, 5, 6, 7, 8, 9. Now if I'm fluorine, my outer shell is the one I'm concerned about. My outer shell has 7 electrons in it. Now, is it going to be easier for fluorine to get rid of all 7 of those electrons, or for fluorine to gain 1 electron? What do we think? Get rid of 7 or gain 1? What is easier for fluorine to do? Now, asking the next question beyond that is, if fluorine decides to get rid of a bunch or gain 1, what is the new charge it's going to have? So, you guys are right. Fluorine's going to gain 1 electron to fill its outer shell because it only needs 1 to have that full 8. So if it gains 1, it's going to look like this. You can see that the new electron's this little blue dot here. Now, before it had 9 protons and 9 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, but it gained an electron. So now it has 9 protons and 10 electrons. So because it gained a negative charge, it gained an electron, this fluorine will now have an overall charge of -1. So that is an ion. So on the right here, or left, I suppose, this is a fluorine atom. It has 9 protons, it has 9 electrons. On the other side, we have a fluorine ion. It has 9 protons and it has 10 electrons. So in an atom, the number of protons and electrons is the same. That's what we call an atom. When we talk about an ion, it has a charge. The protons and electrons aren't the same. You either have extra electrons or you either have extra protons. So fluorine will always gain an electron and will always have an overall charge of -1. Just because that's the easiest darn thing for fluorine to do. And now that fluorine's gained that electron, it looks like neon because they are the same thing. They have the same outer shell. So it's trying to look like its closest noble gas, which is neon. All right, let's look at a few more ions and then we'll look at wrapping up for the day. So let's do a couple more examples. I'm just going to jump back over to my notebook here. All right, let's talk about some ions. Lost my pen, found my pen. I'm going to pick something like, let's start with something easy. Let's look at lithium. Lithium is element number 3 on the periodic table. All right, so atomic number is 3, and its atomic mass is 6.9. And we're going to round that to 7 because it's close to 7. We'll call it 7. All right. In the middle, there are 3 protons, and then the mass of the nucleus is 7. So 3 of those 7 are protons. What's left? Well, if we go 7 minus 3, we end up with 4, and that's the number of neutrons. So what I'm going to do is draw a lithium atom. So lithium is Li. Here's my atom. And I'm going to draw a lithium ion. All right, so in the nucleus, I have 3 protons and 4 neutrons. For both an atom and an ion, that is the exact same. So the nucleus for atoms and ions are identical. If we change the number of protons, it would just become a new element. So that wouldn't work very well. So for an atom, I have 3 protons. I'm going to also have 3 electrons. So we know the first shell can hold 2, 1, 2. I need 3, so I'm going to add 1 more. There we go. 3. Now, if I'm lithium, am I going to gain to fill up my outer shell? Remember that outer shell, the valence shell for lithium there, can hold 8. So is it going to gain 7? Or lose 1? What's going to be easiest for it? think of it as just being really lazy. It's going to lose 1, for sure. It's going to lose 1, yeah. Of course it's going to lose 1. All right, so I'm going to draw it again over here. Sorry, need a new shell. All right, so in the inside here I had 1, 2, and then the next shell. I had that third one. But you guys all said, hey, Mr. Borden, it's going to lose 1. So we're going to get rid of it. Gone. Now that other shell is empty, so I can just get rid of that as well. There we go. So now that lithium has lost 1 electron, decided to get rid of it, it has 3 protons, and it has only 2 electrons. So is the charge unbalanced? Yes, that's why we call it an ion. What is the unbalanced charge? What do I have extra of? Do I have extra protons or do I have extra electrons? Is this thing going to have an overall charge of positive, or is this going to have an overall charge being negative? Well, if I have 3 protons, that's 3 positive charges. 1, 2, 3. And I only have 2 negative charges, of course not drawn to scale. What am I going to be left with? Well, 1 positive cancels out with a negative, another positive cancels out with a negative, and I'm left with 1 extra positive charge. So when I draw my ions, so far we haven't done this, but this is a good habit to get into. What we do is we put these giant brackets around it. Giant brackets. And up here in the top corner, we write the overall charge that this thing has. So we are saying that this thing has a charge of +1 because it has 1 extra proton. Because it lost a negative charge, it now has an overall +1 charge. So this is what the ion is going to look like. We're going to draw our ions like this. Big square brackets, positive charges next to it or negative as the case may be. So we'll look at some other examples of ions next day. Look at some more. So for now, we're going to leave it like that. I'm going to jump into the learning guide and kind of show you what I'd like you guys to do for next day's work. Just kind of some stuff to get your Bohr models on and remember doing some of these things if you've remembered them from last year. So the learning guide looks like this. So we've done some of these notes. We've done some of the atomic theory bonding stuff. We did the nucleus. We did the periodic table. And then you guys talked about ions a little bit. So we've just kind of touched on ions. We haven't really done a ton of that stuff yet. We didn't get to patterns in the periodic table, so we're just going to leave the notes at that spot for now. But down at the bottom, there's some practice questions. All right, so this is on page 8. And on page 8, it says, practice atomic theory and bonding. So you should be able to do the first 3 questions. And then 5, 6, yep. Should be good for there. And you're good up to 8 and 9. So question 9, it's talking about atoms. Now, hopefully I haven't confused the idea of atoms and ions. But it wants you to draw the Bohr model for boron. It wants you to draw the Bohr model for aluminum. I think there are a few extras on the next page as well. So boron, neutron, boron, aluminum, nitrogen, phosphorus on page 10. Number 10, you won't be able to answer right now, so skip for now. And then number 11 asks you to draw some ions. So this is number 11 on page 11. You should be able to complete up to the bottom of page 11. So that's where we're gonna leave you for now. Yeah, Abby, I have to teach class at KSS in a few minutes here, so I'm gonna jump over to my other role. So the schedule is a bit wonky in terms of what's going on. You won't have any more class today, that's it for today. It was scheduled for me to be 2.5 hours long, but we won't have that because everybody else is teaching and I have to teach at KSS. Tomorrow it says 2 hours of social studies or 2.5 hours of social studies. What we're gonna do is, first thing in the morning is gonna be social studies, and then at 10:30, I'm gonna jump in for an hour and we'll continue on with where we've left off today. Now, I have been really lenient so far with you guys getting work done on time. And I've been harping on you to get the first 3 units done and to get unit 10 done. Some of you have, some of you haven't. When we get into this chemistry stuff, if you do not keep up with us, you will get left behind very quickly. We're gonna move quickly through it because we just have no choice. We don't see each other that often, twice a week. So I'm gonna have to motor through this stuff, but if you're not keeping up, if you're not doing the little tiny bits of work each day, if you just sit down and try to do it all at the end of the week, you will be absolutely lost. And I don't want that to happen. Chemistry is kind of like math. It's scaffolded. If you don't get the foundation stuff, the things we're going to do tomorrow is just going to be way beyond you. And the things we're going to do the next day is going to be even more difficult. And then once we get to the very end, if you don't understand how to do the stuff at the very beginning, the very end is going to be like an absolute different language. So I can't stress it enough. At the end of each of these classes, when I say go through and draw the Bohr models, do the work, please do it. You have to. If you don't, this chemistry stuff's going to leave you in the dust. So I wanted you guys to all have a fresh start in chemistry, and hopefully you've done all the old stuff, the biology and things like that. But if not, get it done and keep up with the chemistry. If you get behind in the chemistry, it's just, that's the end of the story. You'll be toast. And it's such a big part of the class. So I'm gonna leave it there. I want you guys to do these practice problems. You were expecting class for 2.5 hours today. I only was on for an hour and a bit. So you have plenty of time to do these few pages of practice. Please do them. If you have questions, come back with them next day, tomorrow. And yeah, essentially everything's kind of like grade 9. There's nothing really different than what you did in grade 9. Some of you may have talked about ions in grade 9, some of you maybe not. We're going to continue on with ions, bonding, Lewis dot diagrams next day. So that's where we're at. I have to run. Get that stuff done. If you have questions, let me know. And hopefully you don't. Hopefully you remember it from grade 9. But do them. Actually do them. If you aren't doing these things, you will not understand them. I guarantee you that. So have a great afternoon. Enjoy the sunshine out there once you're done your science. And we'll see you guys tomorrow. Thanks.